Base. Oh. Base allowed ko man sa load ya Ha? Wala man. Wala ko kabalo, G. Base wala na sila, teacher. Okay, so I hope you could see my screen now. Actually, in this particular module, you will have two sets of slides. One for physical examples of first order systems, and the other one is for the physical systems arranged in series. So there are two modes or two different arrangements of these physical systems arranged in series, and that would be our next set of slides. So this will be our first slide, which will be covering only the physical systems that we will limit ourselves into in terms of the application of modeling using differential equations on these particular physical systems. Okay, so let me proceed. Now, with the physical examples of first order systems or systems that can be modeled using first order differential equations, we start with the liquid level system. So in here, we're trying to monitor changes in the level of the liquid inside the tank for changes in the volumetric inflow or the amount of fluid that is entering our tank. So in this case, we have two very important assumptions before we go to the model differential equation. So in here, we assume that the cross-sectional area of the tank is a constant and the density of the liquid as well is constant in this case. Now, as to our representations and what the representations rather that you see also in the in Kauhanor. So your Q sub O there represents there's a typo error here, class. It's volumetric flow rate through the linear resistance R. So it's this R in here, and the volumetric flow rate passing through this particular linear resistance is Q sub O. Now we say that is linear resistance because the relationship of the head or the level of the liquid inside the tank to the volumetric flow rate through this resistance is linear, and it's given by this particular equation. So your Q sub O is equal to H over R. H is the level of the liquid and R is the flow resistance. Now, speaking of the flow resistance, it would come in the form of the pipe itself. The pipe itself can also offer resistance to flow, or it could also be in the form of a weir or a valve. Okay, so the problem will make it known as to what type of resistance it is and what would be the corresponding relationship of the resistance to the volumetric flow through it and to the head. If this is not given, the problem will give you a particular scenario or condition that will allow you to determine the linear equation that will determine the relationship between head and this volumetric outflow through this particular resistance. So most of the time, the problem gives you this relationship. If not, it will give you a way of determining this relationship. But as long as our system is a linear system, then we have this particular linear equation. Now, since our systems, the systems that you will encounter later on in the industry are all not in steady state condition, there will be at some point a condition wherein the particular process variable will be experiencing what we call unsteady state. So in this case, we will perform unsteady state mass balance for our liquid level system. So in this unsteady state mass balance, the rate of accumulation of the mass in our tank is equated to the difference in the mass flow into the tank and the mass flow out of the tank. So this is your representation for that. Your A times the derivative of the level with respect to time is your rate of accumulation. Q is the volumetric flow rate to the tank, and Q sub O is the volumetric flow rate through the linear resistance. Now, at steady state, we expect that there won't be any disturbances, or there won't be any changes in our volumetric flow rate to the tank, and that's your Q. And at steady state, since it's not going to change, we expect that our volumetric flow rate through the linear resistance should also be equal to it. Why? It's because at steady state, we expect that the volume and the level as well of the liquid inside the tank will be kept constant. Now, if these two are not equal, then there would come a time that the level of the liquid inside the tank will decrease up to the point that your tank will go empty, or it will either overflow. Okay, if the volumetric through your linear resistance is smaller in value than the volumetric flow rate of the fluid that is entering the tank. So two different scenarios if your Q is not equal to Q sub O. Either you have the tank going empty, or the tank or the fluid inside the tank going to overflow. Okay, now we proceed to the next slide. So more on the linear resistances. So a pipe, as I have mentioned a while ago, can be considered also as a linear resistance. Now, this is in the case when your flow is on the laminar range. Now, a contoured weir, we call a suture weir, can also produce what we call a linear head flow relationship. So if it's a linear head flow relationship, it's comparable to Q sub O equal to H over R. Okay, that was the equation shown to you in here. Okay, so linear. So if I place a constant in here, for example, a 10, a 20, or a -2, or something like that, it's still linear because the equation is still comparable to the equation of a line. Okay, now for turbulent flow, so it was mentioned here that if the flow is on the laminar range, your relationship between head and resistance is linear. So for turbulent flow through pipes and valves, generally your Q sub O is proportional to the square root of the head, or the level of the liquid inside the tank. Now, flow through weirs, on the other hand, having simple geometric shapes, can be expressed as KH raised to N, where this K and this N are positive constants. Now, flow through, on the other hand, of a rectangular shaped weir is proportional to H raised to 3 halves. Now, in this form class, H raised to 3 halves, or KH raised to N, or H raised to 1/2, all of which the corresponding differential equation now will be nonlinear. And it will not go through the usual way of determining the transfer function for that particular physical system, because you have a particular term in your differential equation which is nonlinear. So that's the time that we use what we call linearization. We substitute an approximate representation for the nonlinear term in your model differential equation to a linear term that will make it possible for you to, of course, follow through or monitor the changes in the level of the fluid inside the tank in terms of changes in the volumetric inflow. So remember that you are only allowed to use Laplace transformation for a model differential equation which is linear. If it's not linear, then you need to do linearization first, which is the last part of this set of slides. Now we go to the transfer function of the liquid level system. And if you notice in this slide, you don't see any derivation anymore as to what is the process or what would be the process in which we can get this particular transfer function of the liquid level system. So this is the transfer function of a liquid level system that relates the head or the level of the liquid inside the tank to changes in the volumetric flow into the tank. Okay, just give a sorry about that background. It's really too loud. Okay, now for the transfer function of a liquid level system relating head to flow changes, it's comparable to that of the first order system, the thermometer that we have used, because your denominator here is similar to that. The difference is the steady state gain that is written in the numerator. So for your thermometer, this numerator here, the steady state gain in the numerator is just 1. But in the case of this liquid level system, your steady state gain is R. Now, the steady state gain is to be viewed as actually the same with the thermometer as the ultimate change in the level. In the case of the thermometer, it's the ultimate change in the reading of the thermometer for a unit step change in the input. In the case of the liquid level system, your input is this one, the Q of T, the changes in the volumetric flow into the tank. In the case of the thermometer, your input is the changes in the temperature of the environment, or of, let's say, for example, of the bath where your thermometer is placed into. So nonetheless, whether we speak of head to flow relationship or temperature to temperature relationship in the case of the thermometer, your steady state gain always is the ultimate change in your output, whatever that output may be, for a unit step change in the input. Okay, so take note of that. Now, this R can also be viewed as the conversion factor that relates your head to volumetric flow rate when the system is at steady state. Now, for a liquid level system, the tau that you are seeing here is equal to this one, the product of the area times the linear resistance R. So that's your tau. As to how this particular transfer function came about for your liquid level system, I'd like to show you the derivation. It's a short process, and the rest of the derivations I will leave to you as an exercise. So let me stop sharing for now. Let's see if you can still remember the measuring tools. Okay, number one, what measuring tool should I use if I want to measure the mass of the avocado? Okay, let's see who was able to read their Kauhanor in advance regarding derivation of the transfer function of a particular physical system, the liquid level system. So let me share the board. Okay, so for your liquid level system, as also presented to you in the slide, I will just start with the model DE. So this is your accumulation term. And this is your Q, the volumetric flow into the tank, and your Q sub O. Okay. Now, if the relationship between head and volumetric flow rate through the resistance is linear, then we can change this Q sub O here in terms of H and R. It's because our unknown function here is H and our independent variable here is T. So we cannot have more than 2 variables to consider when we are determining the transfer function. So it's a must that this Q sub O here, should be changed to this relationship. That way, I will only be, shall I say, comparing or establishing the proper word is establishing the relationship between the level and changes in the volumetric inflow of the tank. So in this case, you will have Q minus, you change this one to H over R. So this is your model equation now. That way, I will only relate Q to H or vice versa. Now, then at steady state, we have the level of the liquid inside the tank not changing at steady state. So dH dt here is equal to 0. So that would be 0, and you have Q sub S minus HS over R. The subscript S that you are seeing here represents steady state condition. So what you're going to do next, just like what you did with the thermometer, is you subtract the two equations. So you have A dH dt equal to Q minus QS minus 1 over R. I'd like to factor out the common constant for the two that I need to subtract, the 1 over R, and I will have H minus HS. I think it's already forthcoming what I'm supposed to do in here because I already have in here deviation variables. So if we let capital Q to be Q minus Q sub S, all in small letters, and capital H to be H minus H sub S. So this equation of yours now, okay, will be A dH dt equal to Q minus H. Okay, I changed the small letter representations here, this one into capital letters. So in here, I will be needing the R in the denominator. Now, if you notice, class, this is already deviation variable. This one is deviation variable, but still we have here a small h in the derivative of the h with respect to time. We can change your d small h dt to d capital H dt. We are allowed to do that because you have the H represented by the capital H in here represented by H minus HS dt. Now, if you're going to perform differentiation to this a difference of H minus HS, this one will have a derivative of 0 because that's a constant, steady state level of the liquid. So your D capital H then is just the same as your D or just equal to your D small h, as you can see in here. So I'd like to change this one now to capital H, and you have now everything in deviation variables. You cannot perform Laplace transformation to any model differential equation that you're using for your system unless your variables or the variables that you're going to relate are in deviation form. So they are to be in deviation form already. So now you're ready to take the Laplace transform. So in this case, I will perform Laplace transform to the derivative of h with respect to t, capital H that is. So I will have S, H of S, minus H of 0. Now for that one, you will have Q of S minus H of S. Now this one, your H, this capital H actually could be interpreted as H minus HS at time equal to 0. So at the starting point in which your disturbance occurred, actually, we don't have a system that automatically feels the disturbance or registers the corresponding change in the variable when the input has already changed. So what I mean is, at the start of the disturbance, this H does not change first. At that very instance. It's not something instantaneous. So at time equal to 0, this H minus HS is still equal to 0. And this one is actually your capital H at time equal to 0. So then this is a 0. So if you will simplify further, that will give us a left side, which is AS, H of S equal to Q of S minus H of S over R. Now I'll transfer this on the left side because that's where I have the h of s. And I like to factor out the presence of the h of s in the two terms on the left. So I will have as plus 1 over r. That's after this one is transferred on the left already. I will have the product of A and S for this one, and I will have 1 over R for this one. The right side is still Q of S. Now, if you simplify this, this would be ARS plus 1. And that would be all over R. And this is multiplied to H of S. And you have here, sorry. And this is equal to Q of S. So in terms of the transfer function that we'd like to have, so output over input. So our output here is level, our input is Q of S, changes in the volumetric flow rate into the tank of the fluid that is entering the tank rather. So you will have H of S over Q of S equal to, so in this case, if you see here, this R goes up and this expression goes down. So you'll have R over ARS plus 1. So as such, we have defined that if this particular transfer function is comparable to in form to the transfer function of the thermometer, then it would be R over tau S plus 1, where your tau is equal to A times R. So this is the transfer function of your liquid level system that relates the level of the liquid inside the tank to changes in the flow rate of the liquid entering the tank. Okay? Any question as to the derivation of the transfer function in here? So your R is said to be the steady state gain for this system, the ultimate value of the change in the level of the liquid when your system is subjected to a unit step change in the input, which is your Q of T. Any question? Okay, if there's none, we'll go back to our slide. So this is our transfer function already. And if we are to relate not the head, but the volumetric flow rate through your linear resistance to Q of S, it's quite easy. So now you could see that your steady state gain is 1, just like in the thermometer. Now, in that case, all you have to do, so from the transfer function that we have derived in here, so this is the transfer function that we have. So let's say that's equation 1. We have actually the equation Q sub O being equal to H over R. So if you're going to evaluate this at steady state, this would be QOS equal to HS over R. If you're going to get the difference, you will have Q sub O minus Q sub OS equal to 1 over R H minus HS. Now, your deviation variable here will have a new deviation variable in the form of capital Q sub O. And that's the small Q sub O minus Q sub OS. This one we have already represented it in the previous derivation. So your equation here now becomes Q sub O equal to 1 over R H of S. Here, okay, we change your difference of the current value of your variable from its steady state value, whatever that variable may be. So in here, it's Q sub O, in here, that's H. Okay, so that's it. So if you're going to perform Laplace transform to this, because anyhow, your variables are already in deviation form, you have Q sub O of S equal to 1 over R. By the way, it doesn't have still your H, your S here. This is just but your level. Okay, so it's after you have performed the Laplace transformation that you will have the level here expressed in terms of HS. So if I want to change the HS, in my original transfer function in terms of Q sub O, that would be then the product of your linear resistance and the Q sub O of S. Okay? So in here, you can see we can change the H of S here to R Q sub O of S. So from 1, your R Q sub O of S divided by Q of S is equal to R over tau S plus 1. So you can cancel out the R's, leaving you with this particular relationship between flow rate through the linear resistance and changes to the volumetric flow rate of the liquid entering your tank. So you take the steady state gain R or the linear resistance R in the numerator and replace it by 1. In the case of um, this liquid level system in which you are relating the volumetric flow rate through the resistance to Q of S. Okay, so you have this. Okay, now we also have another scenario still for the liquid level system wherein your flow rate is from the tank is regulated in the form of a pump or regulated by a pump. So in this case, there won't be any changes to it because as to the pump, it sets to deliver the volume of fluid in which you have set it to deliver. What I'm trying to say that your Q sub O here, it's written actually in here, your Q sub O is a constant. So in this case, when you derive the transfer function, I will leave that to you as an exercise. You will have a very simple transfer function relating H of S to Q of S. Okay, so you have it now 1 over the product of AS only. So that's only for this case wherein your volumetric flow rate from the tank is being regulated by a pump. Okay, now you proceed. Any questions so far? Okay, there's none. We will continue. So as for the mixing process, so in here, you have a fluid also in the tank. And these are our assumptions here, very important assumptions. It's at constant density. The fluid inside the tank at any time is at constant volume. And take note, unlike the liquid level system, your volumetric flow rate to and from the tank has to be constant as well. Because this time we're trying to measure the corresponding change in the concentration of the fluid leaving the tank to changes in the concentration of the fluid that is entering the tank. So excuse me, class, ha? Okay, we'll continue. So that's it for a mixing process. We are going to check the effect of the changes in the concentration of the liquid that is entering the tank to the concentration of the liquid or the fluid that is in the tank, at the same time the concentration of the fluid that is leaving the tank. So these concentrations that I have mentioned should have the unit of mass per unit volume. Okay, anyway, the Q's are defined already in here as volumetric flow rates. Now, if you're going to make an unsteady state mass balance in our mixing process, it's the same thing. We have the rate of accumulation of mass inside the tank should be equal to the rate of mass entering the tank and mass leaving the tank. In that case, you will have the accumulation term now relating the derivative of the product of the volume and the concentration of the fluid inside the tank at any time, and then it has to be expressed per unit time, or it's the derivative of the product of these two with respect to time. Whereas in terms of rate of mass in and out, it's the product of the volumetric flow rates and the concentrations of the liquid in entering the tank and leaving the tank. So you have here Qx minus Qy equal to d of Vy dt. Now, volume, as mentioned in the previous slide, is assumed to be constant. So when you differentiate this expression here, you write, or you can write it before your derivative. So you're simply going to write now the right side of this equation to be dy dt. When you evaluate, just like the way we determined or derived the transfer function for a liquid level system, you will evaluate this original model DE that you have at steady state. So at steady state, there won't be any changes in the concentration of the liquid inside the tank. So the right side becomes 0, and your variables in here will be represented with a subscript S, denoting that these are variables at steady state. When you're going to subtract these two equations, the second one from the first, it will introduce again a new set of deviation variables. So we will represent our x minus xs in small letters to capital X, and our y minus ys to capital Y. In that case, we will have something like this. The rest will be, you need to perform Laplace transformation to this dE. So giving you a transfer function for a mixing process, which is the same as that of the thermometer. Steady state gain is equal to 1, but this time your tau is V over Q. Okay. Now, in the case of the liquid level, your tau is AR. In the case of your thermometer, it's MC over HA. Okay, so the same form in the transfer function, they only differ in the transfer, in the time constant. Okay, that's for our mixing process. Now, for the stirred tank heater, this was used originally to illustrate the process of determining the transfer function when we were discussing it as an intro to, let's say, module 1, I think. So this is our stirred tank heater. For this stirred tank heater, we will assume again that the volume of the fluid inside the tank is kept constant, and the W, the mass flow rate of the liquid entering the tank and leaving the tank, is also constant. So what we're going to account for in here would be the changes in the temperature of the fluid inside the tank, same as that of the fluid leaving the tank, in relation to changes in the inlet temperature of the fluid and the amount of heat that is being supplied to the tank. So since this is a stirred tank heater, your form or your manner of introducing heat to the fluid inside the tank could either be through the use of a heating medium, most oftentimes it's steam, or through the use of your electricity. So you have an electrical heater in that sense. Okay, now if you're going to write the model DE for this stirred tank heater, you will still follow through the same formula, but this time this is comparable to the formula that we have in your kinetics then. So we have rate of energy flow into the tank represented by this one. The rate of energy flow out of the tank represented by this one. So this is for the fluid entering, and this is for the fluid leaving the tank. Q is the amount of heat generated by the process itself or by the heater that is supplied by your heating medium or by your electricity, if it's in the form of electricity, and this is the rate of accumulation of energy inside the tank. So rho Vc, the D of T minus reference temperature. Now this reference temperature depends on the unit in which you're working on. If you're working on SI units, this is 0. If you're working on English units, this is 32. So just like the way you do it in your unit ops. So reference temperature is 0 unless otherwise the problem says that you use a reference temperature of 25. But if the problem is silent about it, if it's SI, your reference temperature is 0 and 32 for English. Now, if this original equation that we have is evaluated again at steady state, there won't be any changes in the temperature of the fluid inside the tank. Then your right side becomes 0. And we have this one now. These two we cancel out because we are subtracting this one. So that leaves us with this. We have the Q and we have this one as 0. If we subtract 2 from 1, you will have something like this. If you recall our discussion then in, I think that was module 1 on the overview of process control and how to determine the transfer function, you cannot determine the transfer function of a stirred tank heater unless you assume something. So it's either you assume that there won't be any changes in the amount of heat that is being supplied to the tank, or there won't be any changes in the inlet temperature of the fluid that is entering your heater. Okay, so you can only relate your T, the temperature of the fluid inside the tank, to changes in the inlet temperature or changes in the amount of heat that is introduced into your tank. So not that you relate the temperature to changes of these two. That in that case, you will really have, if you have changes in both the inlet temperature and the amount of heat that is introduced into the tank, you will not be working on with a transfer function. You will really be working on the D itself because you already have two variables that are not that are both changing, which would affect the behavior of the variable that you're trying to monitor or measure. Okay. Now, in here, as an example, if we assume that there aren't any changes in the inlet temperature, then we will just have Q, changes in the amount of heat that is introduced into your tank, and your T minus Ts is represented this time by T prime. Okay, now your equation 3 in here, this equation 3 becomes equation 4. So notice that we don't have anymore the Q. It's here, by the way, it's still in here. Your T and your Q. Now, if we take Laplace transform of this equation, we have this. And if we rearrange equation 5, producing the following first order transfer function relating your T to Q. So as I have mentioned, it's assumed that in here there are no changes in the inlet temperature of the fluid that is entering your tank. So if it's the other way around, if it's the Q that is not changing and it's the inlet temperature that will be changing, then your transfer function this time will be relating T to T sub I. Okay. This is your transfer function after you do, you transfer this part here to in here so you can group together the D prime of S. And you divide both the entire differential equation by WC to isolate the T prime of S in this side. So that will introduce 1 over WC in your numerator, which now will represent the steady state gain for our stirred tank heater. We try to make our transfer function, since this is an example of a first order system, we try to make our transfer function conform to that of a first order system as well. And it's important that you have a denominator in the form of a tau s plus 1. So that's the very purpose why you need to divide by WC. That way, your denominator would be something like this. Okay? Now, this is the transfer function of your stirred tank heater where inlet temperature changes are not accounted for or is negligible or said to be zero. So we only related it to changes in the amount of heat that is supplied to your tank. Okay. Now, the process of linearization is the part wherein I've mentioned a while ago, a term in your differential equation is not anymore linear. So if the relationship between flow through the linear resistance would require that your H now will have an exponent other than 1, then you need to linearize a particular term if that's the case. We cannot go on with the usual procedure of determining the transfer function if there's a particular term in your DE that is not linear or has an exponent. The variable that we're referring to is in here, for example, is the H in the liquid level system has an exponent other than 1. Okay. Okay, 10 minutes. So we'll finish this and I'll leave everything to you to study. We'll have specific examples rather next meeting. And that would be Thursday next week. Okay. Now, if you have a liquid level system in the case that you are seeing here, where the relationship of your level H to Q sub O is not linear, you have something like this, there's a need for you to linearize your DE. So how do we do the linearization? So if your Q sub O is represented as this, the very simple first order DE then that I have shown to you, which is just ADHDT equal to Q. By the way, this is just Q then. Now it's represented in here as Q sub I equal to Q sub O. Your Q sub O being C sub V, or rather minus Q sub O, where your Q sub O is C sub V square root of H. So we cannot do the next steps because of this nonlinear term. We have to replace it with something that is linear. So the approximate replacement of this uses Taylor series expansion. Now, in this case, your Q sub O will be replaced by this infinite series of terms. The first one will be your Q sub O evaluated at steady state. Now, you see this H sub S here. This is to be read as Q sub O at the evaluated at the value of the level at steady state condition. So Q sub O of H sub S. The next terms will have the derivative of this Q sub O expression multiplied to the different deviation variables raised to the exponent equivalent to the order of the derivative divided by the factorial of the said order of the derivative. So this one here, so this would be your first derivative. So it's raised to 1 over 1 factorial. This is the second derivative of Q sub O evaluated at H sub S. Now we multiply it to the deviation variable H minus HS raised to 2, and this is 2 factorial. You're going to include here the rest of the terms because this one is an infinite series of terms. You will have to increase, or there's going to be an increase in the order of the differentiation of your nonlinear Q sub O expression. And all the more that the deviation variables here will be raised to an even higher exponent and will be divided by a greater number. Because next to this is 3 factorial, then 4 factorial, and so on and so forth. If this was discussed in your calculus then, in your integral calculus, if this was reached, this part is reached, you will notice that as we increase the terms in here, the value of the terms are negligible compared to the first two. Why do we say that the rest of the terms in the infinite series of terms will have an, shall I say, a negligible value compared to the first two? It's primarily because of the denominator. The denominator will be increasing in terms of factorial, and as such, the value of this thing decreases because you're going to increase the value of the divisor. So, but that's not the reason why, class, in here we did not write the term which has the second derivative, the third derivative, and so on. The reason here is that aside from the fact that its value is negligible to the first two, you have here already h minus hs raised to 2. This makes h, our level, also nonlinear because of the exponent 2. So we eliminate all nonlinear terms in this approximation for the Q sub O. So in that case, you will only include the first two. And the original Q sub O that you have here, which you will substitute in here in our original DE, will be replaced by this approximation. So you change CV square root of H to the two terms that you are seeing on the right side of equation 3. Okay, so taking the derivative of 1, so you take the derivative of this C v sub V, by the way, is a constant dependent on your valve. It's a valve constant. And that would be CV. This one is 1/2 H raised to negative 1/2. And since you are evaluating the derivative of this Q sub O in equation 1 at steady state, then you will place here Q prime or Q sub O prime at H sub S is equal to 1/2. This should be C sub V, class. I took this V. C sub V, H sub S raised to negative 1/2. This one, the 1/2 C sub HS raised to negative 1/2 will be substituted in here in the Q sub O prime at H sub S. So if we move further in our derivation, you will have this particular equation now. Substituting 4 to 3. So this 4 is substituted to equation 3. So your equation 3 becomes this one, equation 5. Okay? If you notice, there is a new constant in here in the form of 1 over r sub 1. And this is equivalent to actually the derivative of your Q sub O. The constants that appear in the derivative of your Q sub O. We say these are constants because your H sub S is the steady state level of the liquid. So it's a constant. Okay, if we substitute this equation 5 in the second term, what do we mean, Miss Ali? Ini siya, islan mo na sang bilog ni nga equation 5. This one, it has two terms. It will give you this particular equation. Okay. Now, if you look very closely, you have here volumetric flow rate to the tank, and this is volumetric flow rate through the linear resistance. So then, however, if you're going to look at it very closely, you cannot represent this by one deviation variable because this one is a different variable than your Q sub O. So, but then we know that at steady state, the level, the volumetric flow rate through the linear resistance, which is your Q sub OS, is equal to the volumetric flow rate to the tank because it's at steady state. So whatever comes in, comes out. So you change the Q sub OS here to Q sub S. So your equation 6 becomes this, which I think you know already what's the next step. This could be represented by a deviation variable. This could be represented by another deviation variable. This could be replaced by capital H. So you have now this one. Okay, the transfer function of your liquid level system in which the linear relationship, or there is no linear relationship in this case, between level and volumetric flow rate through the linear resistance. So the difference of this particular transfer function for a nonlinear relationship between Q sub O and H with the one which has linear relationship is just in the numerator. So if there is linear relationship between Q sub O and H, this is just R. But if it's not linear, this is now R sub 1. And what is that R sub 1? So we get it from 1 over R sub 1 to C times H sub S raised to negative 1/2 that we had here, in here. Rather, 1/2 CH raised to negative 1/2. So this will be the corresponding value of R sub 1. So your R sub 1 is a constant that will need the valve constant and the steady state level of the liquid. Your tau is not AR, but rather AR sub 1. This is in the case wherein, as I've said, you need to linearize because you cannot apply the linear relationship Q sub O equal to H over R to your system. Okay? So this is how you go about applying, determining the transfer function of a particular system using Laplace transformation other than the system that we have discussed before, which is the thermometer. So now you have the liquid level with 3 different scenarios and the mixing process and the stirred tank heater to be added to the thermometer as the system. Now, we will end with these 2 terms. This is the terms that are introduced in that part of the chapter. I think this is chapter 6 of your book by Kauhanor. The term non-regulation and regulation. So when you speak of non-regulation, so this is a condition where the response of the system grows without limit. The response grows without limit for a sustained change in the input. On the other hand, when you speak of regulation, a condition for systems that have a limited response for a sustained change in the input. This is always the case, and a very simple example for this is the step input. So it's a regulated system if we have a step input. A non-regulated system is like for a system which is subjected to a ramp input. Okay? So this is the last part of our slide now. Okay, it's 10:31. I can cater to questions if you have questions. Do you have any questions, class? No questions. So for let's to stop recording here.